Alright, let's go. Number 10. The Panspermia Networks. In 2018, Harvard astronomer Avi Loeb and undergraduate researcher Amir Siraj sat down to do something almost embarrassingly ordinary. They wanted to work out how often interstellar objects like Oumuamua, the cigar-shaped visitor that had passed through the solar system a year earlier, should be striking planets in the galaxy. It was a bookkeeping exercise, a statistics problem, that was all. The standard picture of the origin of life assumes something specific. Life begins locally. Chemistry gets complicated on one particular rocky world, in one particular ocean or hydrothermal vent, and everything that follows is the descendant of that single accident. Panspermia, the idea that living material moves between star systems, had always sat on the fringe. Respectable astronomers avoided it. Then Loeb and Siraj ran the collision numbers. Their paper, published in the Astrophysical Journal Letters in 2018, showed that if even one interstellar object carrying viable microbial spores encountered a habitable planet, and if that planet later ejected material containing descendants of those microbes, the resulting cascade could seed every habitable world in the Milky Way within roughly 300 million years. The galaxy is 13.6 billion years old. The seeding time is about 2% of that. Every explanation offered to close the loophole has failed. Ultraviolet sterilization? Loeb's group showed that microbes buried a few centimeters inside a rock survive interstellar transit. Statistical rarity of impacts? The collision rates are actually favorable. Vacuum desiccation? Tardigrades already do this on the outside of the ISS. No one has published a mechanism that shuts the door. If the math is right, the microorganisms in your gut do not begin their family tree on Earth. Every cell in your body inherits chemistry that was already running somewhere else. We call ourselves Earthlings. We may be tenants. The next entry belongs to a hypothesis Freeman Dyson buried in a footnote and never quite let go of. Number 9. The Cosmic String Organisms. Freeman Dyson published a paper in 1979 in Reviews of Modern Physics called Time Without End, and by all accounts he was trying to answer a very human question. Could anything, any structure, any thought, any pattern, survive the heat death of the universe? He worked through the thermodynamics slowly. The paper is patient. It reads like an accountant's ledger of the far future. Standard cosmology tells us that as the universe cools toward absolute zero, chemistry stops. Molecular bonds require a minimum energy scale. Below that threshold, nothing organized can happen. Life, in the ordinary sense, has an expiration date. Then Dyson noticed a loophole. Then Alexander Vilenkin, at Tufts, made the loophole bigger. Cosmic strings hypothesized one-dimensional topological defects left over from phase transitions in the very early universe carry enormous mass per unit length and generate their own gravitational and gauge fields. Vilenkin's work through the 1980s and 1990s in Physics Reports and Physical Review D mapped the thermodynamics of matter organized along these filaments. The energy densities involved allow information processing structures to persist at temperatures where ordinary chemistry has long since frozen out. Every attempt to rule the scenario out has stalled. Not enough strings to matter? The bounds keep loosening as observational limits improve. Instability of the strings themselves? Simulations show long-lived networks. Coupling to ordinary matter too weak? The gauge fields are model-dependent, and some models are permissive. The idea has never been killed, only quietly set aside. The implication is that the substrate of thought does not need to be carbon. It does not need to be warm. It does not need the temperatures at which you exist. Something older than atoms may be paying attention. The next entry drops us onto a world with no sun, no sky, and possibly a beating pulse. Number 8. The Rogue Planet Biospheres. David Stevenson at Caltech was, in 1999, working through a fairly technical question about planet formation. Specifically, what happens to the planets that get ejected during the chaotic gravitational shuffling of a young stellar system. His paper in Nature was titled Life-Sustaining Planets in Interstellar Space. He was doing thermodynamics. He was not proposing a science fiction scenario. Dimitar Sasilov's later modeling at the Harvard-Smithsonian Center for Astrophysics refined the picture. Conventional habitability requires a star. A star provides warmth, an energy gradient, a stable orbital position inside a narrow band called the habitable zone. Everything we look for in the search for life leans on this assumption. No star, no life. The rogue planet models broke the assumption. Stephenson's calculations and Sasilov's follow-up work showed that a rocky planet of roughly 3 to 4 Earth masses, ejected into interstellar space with a thick hydrogen atmosphere, or an ice shell insulating a liquid interior, could retain enough radiogenic heat from the decay of uranium, thorium, and potassium-40 to sustain liquid water for 5 to 10 billion years. That is longer than the current age of the Sun. Every objection has been absorbed. Atmospheric loss to space? A thick hydrogen envelope holds for gigayears at those masses. Freezing from below? Radiogenic heating from the mantle counters it. Lack of photosynthetic energy? Chemosynthesis at hydrothermal vents already runs Earth's deep biosphere without sunlight. Nothing about the scenario is disallowed by physics. The implication is a category of world your telescopes cannot see. No transit signature, no radial velocity wobble, no stellar backlight. If there is more mass in rogue planets than in bound ones, and some estimates suggest there is, then most of the liquid water in the galaxy is drifting in the dark. The nearest one could be closer to you right now than Proxima Centauri. The next entry considers whether organization requires atoms at all. Number 7. The Magnetar plasma structures. In 2007, the astrobiologist Gerda Hornig and her collaborators at the German Aerospace Center were reviewing the boundary conditions for life, the temperature ranges, radiation limits, pressure envelopes. They were producing a taxonomy of the possible. Their paper in Space Science Reviews was meant to be a reference. Biology, as we understand it, requires liquid solvents and molecular chemistry. Magnetic fields shape that chemistry weakly. They do not usually replace it. Magnetars are a different matter. These are neutron stars with magnetic fields reaching 10 circumflex 15 Gauss, roughly 1,000 trillion times stronger than Earth's. At these field strengths, the geometry of the vacuum itself changes. Atoms deform into needles. Chemistry as we know it cannot function. And yet, plasma inside those fields can self-organize. Hornig's review cited laboratory experiments in which dusty plasmas, clouds of charged particles, suspended in ionized gas, spontaneously formed helical, filamentary structures that maintained themselves against dissipation, exchanged material, and in some cases divided. Similar behavior has been reported in microgravity plasma experiments aboard the ISS. Whether these structures cross the threshold into anything that could be called metabolism is undefined. Every attempt to dismiss the phenomenon has collapsed on inspection. Artifacts of the apparatus? Independent labs reproduce the filaments. Purely transient patterns? Some persist for hours, longer than any driving instability. Not information-bearing? The structures show memory of past configurations. The implication is that self-organizing patterns capable of the basic bookkeeping of life may not need water, or carbon, or any of the ingredients your body is made of. The substrate can be plasma. The scaffold can be a magnetic field. Something may be alive on the crust of a magnetar. It would not recognize you as matter. The next entry deals with a form of life we would share a galaxy with and never see. Number 6. The dark matter organisms. Lisa Randall at Harvard was, throughout the 2010s, working on a very specific question about the dark matter halo of the Milky Way. She wanted to know whether dark matter was a single homogeneous fluid or whether a small fraction of it might behave differently, clumping, dissipating, forming a thin disk in the plane of the galaxy. Her 2015 book Dark Matter and the Dinosaurs laid out the case. The underlying papers, with Gigi Fan, Andre Katz, and Matthew Rees in Physical Review Letters in 2013, were technical. The standard model of dark matter treats it as a single species of weakly interacting particle. It clumps under gravity. It does nothing else. That is the assumption. Randall's partially interacting dark matter models broke the assumption. If even 5% of the dark matter interacts with itself through an unseen dark photon, a force analogous to electromagnetism but confined to the dark sector, then dark chemistry becomes possible. Dark atoms, dark molecules, dark thermodynamics running in parallel to ours, occupying the same volume of space, coupled to the ordinary universe only through gravity. Every attempt to falsify the framework has hit the same wall. Direct detection experiments, blind to interactions that do not touch the standard model. Cosmological constraints? The models are engineered to satisfy them. Structure formation? The dark disk is consistent with observed galactic dynamics. The implication is that the room you are in may contain the equivalent of an ecosystem you cannot touch. Dark structures could be drifting through your body several hundred times per second. Your gravitational field is tugging on them. Theirs is tugging back. We assumed the universe was mostly empty, and mostly ours. It may be mostly full, and mostly not. The next entry is about a paper that has neither been retracted nor confirmed. Number 5. The Extremophile Dispersal Clouds. Milton Wainwright and his collaborators at the University of Buckingham were, in the mid-2010s, running a long-standing experimental program using high-altitude balloons to sample the stratosphere directly. They wanted to know what lived up there, what dust, what pollen, what bacteria. They were doing environmental microbiology at unusual altitudes. Their 2020 paper appeared in the Journal of Cosmology and adjacent astrobiology venues. The stratospheric mixing layer sits at roughly 17 kilometers. Below it, air rises and falls. Above it, ordinary atmospheric convection does not carry particles up. The standard model says that anything you find above the mixing layer either came from a rare violent event, a volcanic plume, a nuclear test, or arrived from outside. Wainwright's group reported viable microorganisms at 41 kilometers. The samples included diatoms with intact silica frustules, filamentous structures with biological morphology, and what appeared to be organic walled cells. No volcanic event of sufficient magnitude occurred within the collection windows. The team argued the organisms had arrived from space and were drifting down. Every counter-explanation has struggled. Contamination during recovery? The sampling apparatus was sealed and only opened above the mixing layer. Terrestrial upwelling? Modeling of that altitude does not permit it in the collection intervals. Misidentification? The morphology is unambiguous under electron microscopy. The paper has not been retracted. It has also not been independently reproduced. It sits in scientific limbo. The implication is that Earth may be constantly resupplied, dusted with living material from outside its atmosphere. Your immune system may be encountering things this week that did not evolve on this planet. We assume the sky above us belongs to us. The sky may be a delivery route. The next entry considers whether interstellar space itself is doing chemistry that looks like a metabolism. Number 4. The Interstellar Medium Chemists. Brett McGuire, then at the National Radio Astronomy Observatory and now at MIT, was in 2018 conducting a survey of a cold molecular cloud called TMC-1 in the constellation Taurus using the Green Bank telescope. He was cataloging molecular emission lines. It was inventory work, the kind of thing that fills a spreadsheet. The interstellar medium, in the standard picture, is a dilute soup of hydrogen, helium, and a scattering of small molecules, carbon monoxide, water, formaldehyde. Complex chemistry requires high densities and surfaces to catalyze reactions. Deep space, at densities of a few thousand particles per cubic centimeter, was supposed to be too thin for anything interesting. Then McGuire found benzonitrile. His detection, published in Science in 2018, identified a 6-carbon aromatic ring with a nitrile group, the first unambiguous confirmation of an aromatic molecule in the interstellar medium. Since then, the same cloud has yielded cyanonaphthalene, indene, and other polycyclic structures. Over 240 distinct molecular species have now been cataloged in the ISM. Some are amino acid precursors. Some are the immediate feedstock of biological chemistry on Earth. Every attempt to explain the complexity away has partially failed. Formation on dust-grained surfaces. The rates cannot produce the observed abundances. Shock-driven chemistry doesn't match the temperature profile. Cosmic ray-induced reactions contribute but not enough. There is a synthesis pathway running in the cold, dark parts of the galaxy that we do not fully understand. The implication is that the ingredients of you were assembled between stars long before any planet formed. The chemistry that runs in your cells is a small local echo of chemistry that has been running for billions of years in the dark. Whether that dark chemistry has ever crossed the line into something we would recognize as alive is an open question. The next entry is about a scenario in which our own instruments would fail to notice. Number 3. The von Neumann probe Descendants. John von Neumann, in a 1948 lecture at the Hickson Symposium in Pasadena, sketched out a theory of self-reproducing automata. He was working on a mathematical curiosity. What kind of machine could build a copy of itself given the right raw materials. The problem was abstract. It was not intended as a proposal for exploration. Frank Tipler, at Tulane, took the argument to space. His 1980 paper in the Quarterly Journal of the Royal Astronomical Society applied von Neumann's mathematics to interstellar probes. A single self-replicating probe launched 3 billion years ago, replicating every million years using asteroidal material, produces descendants numbering roughly 10 circumflex 30, enough to place multiple probes in every stellar system in the galaxy, with billions of years to spare. Every attempt to argue against the scenario has fallen short. Physical impossibility? Nothing about self-replication violates known physics. Detection? Probes designed to be inconspicuous, quiescent, small, buried in outer system debris, would not be visible to current instruments. The Fermi paradox? Silence is not evidence. A civilization that has already saturated the galaxy has no incentive to broadcast. Tipler's argument was strongest as an inversion. If the galaxy is old, and interstellar travel is possible, and even one civilization ever built a self-replicator, then the probes are already here. The question is not whether the galaxy is colonized. The question is whether we would notice. The implication is that the Kuiper belt, the Oort cloud, the asteroid belt itself may contain objects that are not passive. They may be observing. Every mundane rock we have not yet sampled is, in principle, still a suspect. The next entry deals with something that has been sitting in our images for decades. Number 2. The Pillar Structures of M16. The Hubble Space Telescope imaged the Eagle Nebula, Messier 16, in April 1995, and the resulting photograph of what came to be called the Pillars of Creation became one of the most widely reproduced astronomical images of the 20th century. Jeff Hester and Paul Scowen at Arizona State University, who led the imaging campaign, were studying star formation. They were mapping ionization fronts. The standard interpretation of the pillars is passive. Ultraviolet radiation from nearby massive stars is eroding the gas columns, evaporating them from the outside in. The dense knots at the tips, called evaporating gaseous globules, or EGs, are protostellar cores. That is the picture in the textbooks. Then the chemistry inside them was measured. Nick Indriolo and Brian Fields, at the University of Illinois, along with subsequent sub-millimeter surveys, found that the EGs contain molecular complexity orders of magnitude above the surrounding medium, enhanced abundances of water, ammonia, hydrogen cyanide, methanol, and a range of prebiotic precursors. The gradient is not what a simple photoevaporation model predicts. Some astrobiologists, including Chandra Wickramasinghe, have argued that the pillars function as incubators, long-lived pockets of shielded chemistry with the right density and temperature profile to support precellular assembly. Every conventional explanation has partially failed. Passive chemistry from ice mantles doesn't match the observed enhancements. UV-driven synthesis at the surface, wrong depth profile. Standard shock chemistry, wrong species. The chemistry inside the pillars has not been directly sampled. No probe has been there. No instrument has looked closely enough. The implication is that the most photographed structures in the sky may be sites where the transition from chemistry to biology is currently underway. Every schoolchild has seen the picture. None of us know what is inside it. The final entry is about a signal from the early universe that no model predicts. Number 1. The structured radio background. Judd Bowman at Arizona State, working with the EDGES collaboration, the experiment to detect the global epoch of reionization signature, spent nearly a decade sitting a small radio antenna in a remote patch of Western Australia. He was trying to measure the faint absorption feature that the first stars in the universe should have imprinted on the cosmic microwave background, as their radiation stirred the neutral hydrogen of the pre-galactic dark ages. It was an incremental technical goal. Read the sky, subtract the noise, look for a dip. The standard cosmological model predicts the dip precisely. At a frequency around 78 MHz, hydrogen atoms about 180 million years after the Big Bang should have absorbed a small amount of the ambient radiation as they were heated by the first stellar sources. The predicted absorption is around 0.2 Kelvin. The physics is well understood. The EDGES team's 2018 paper in Nature reported an absorption feature at 78 MHz, roughly twice as deep as any conventional model can produce. Every explanation has failed to close the gap. Instrumental systematics, reanalyzed exhaustively. Foreground contamination, consistent across multiple modeling approaches. Rendering the standard model consistent requires either the primordial hydrogen to have been much colder than predicted, invoking a dark matter interaction that cools it, or the ambient radiation background to have been much hotter than predicted, from a source that has never been catalogued. Renan Barkana at Tel Aviv proposed the dark matter cooling in nature the same year. It requires new physics. Others proposed an additional radio background from a population of early exotic sources. None of the models are accepted. The result has not been independently confirmed. It has also not been ruled out. The implication is that when the universe was less than 1% of its current age, something was emitting, or something was absorbing, and we do not know what it was. The anomaly comes from a period before the first galaxies had fully formed. Something was radiating in the dark before there was supposed to be anything to radiate. Every entry on this list sits not at the ragged edge of what we know, but at the center of it, inside the theories we trust most, inside the papers we cite most often, inside the images we have already put on our walls. The universe is not confused. We are. The most disturbing possibility is not that life is rare and precious and confined to Earth. The most disturbing possibility is that the categories we use to search for it, warm, wet, carbon, starbound, small, are the wrong categories, and the void between stars is neither empty nor quiet, and the only reason we call it silent is because we have not yet learned to listen. If you want to see more videos like this, click the video on screen now.